Okay, what is quantum metrology? So quantum metrology is, for me, a clever way to use coherence in the first place, and then if you can use coherence, then you may try to think how to use like a meta-coherence, which is entanglement. So if you think about optical interferometry, actually we've been using coherence for a long time without knowing that it's quantum coherence, yes? So like classical interferometry basically uses coherence of light. But we can also be more sophisticated and try to use non-classical states of light, like for example squeezed light, which from certain theoretical perspective can be equivalently viewed as a way to use entanglement between photons, okay, in interferometry. And then to be realistic, we also think what are the dominant decoherence processes. In case of optical interferometry, it's usually photon loss, and we ask how well we can utilize these things, taking into account this, and reach the best sensitivity. So then, if you are more from atomic field, then you can think about, for example, atomic clocks, which are frequency reference for measuring time. And then, for example, lattice clocks or like standard cesium clocks, they basically utilize atoms as if they were independent. So you just, more atoms means stronger signal, but there is no more with it. So you don't utilize entanglement between atoms to improve your sensitivity, while, for example, in principle, you could think about ion clocks, where you have few ions that are prepared in a more fancy state, and again, improve your sensitivity of your clocks. But then again, you have a lot of things to fight with, loss of atoms, so atomic dephasing, and your local oscillator fluctuation. So basically, the thing that you try to couple to your atoms, like laser or microwave generator, which is your element that you will count cycles with, and you couple it to atoms, and because it fluctuates, it also makes things more difficult. Okay, and for example, if you want another example of quantum metrology, then you can think about NV center magnetometry, where you have very long-lived electron spin in NV center, and you can sense magnetic field. In a simpler setup, if you want to be more fancy, you can realize that this electron spin interacts with some nearby nuclear spins, and you can try to entangle them to store your coherence longer, and then in this way improve your sensing. Okay, so this is like a more experimentally flavored slide. And this is what is quantum metrology for theorists. It's maybe less spectacular, but it's also useful. So you think of some evolution quantum channel that depends on the parameter you want to estimate. You send the probe state that evolves according to this evolution. Then you try to measure it. So you have different measurement results I, and then you want to estimate this parameter with some estimator function that depends on the measurement result. And in the end, you ask yourself how to do it optimally. So optimizing over things you have control. So we assume that the channel is given. We cannot control it, but we can control what we send into this channel. We can control how we measure and how we infer the information. We want to perform this estimation as good as possible, so to minimize the variance of our estimation. Okay. So there are some very useful tools to simplify this task, because as you can imagine, if you write something like this, then you don't know where to start. But there are very useful tools, and one of them is Cramer-Rao bound. So classical Cramer-Rao bound tells us that if we have some probabilistic model, so we have some events I that depend on parameter phi, and we ask how we can estimate phi knowing I, then the Cramer-Rao bound tells us that whatever unbiased estimator we choose, where unbiased means that the average value of the estimator will track the true value, we cannot do better than this inequality where the variance of estimation is bounded by 1 over f, where f is the Fisher information. And the Fisher information simply tells you I mean, how much information there is in this probability distribution on the parameter phi. So the bigger the derivative of this p over phi, the bigger the information is. Okay. So, and you have now the quantum version of this Cramer-Rao bound, which does not assume that you already have a probability distribution, but it just assumes you have some quantum state, which you can measure with some optimal measurement. Okay, so these probability distributions now come from actually acting with your measurement operator on your output state, and you get probability distribution. And now you ask yourself, if I want to do optimal measurement and optimal estimation, how well I can do? And this bound tells you cannot do better than this, where the variance of estimation is bounded from below by 1 over quantum Fisher information. Quantum Fisher information is just a function of this output state, okay, from your channel. There is no problem looking for measurements and estimators. You just calculate a function of your output state, and you get a bound. Okay? And for pure states, this formula is very easy. And you can even make it much more familiar to yourself if you realize that in case where your parameter of estimation is time of evolution of a quantum state, okay, so that your psi t is just standard unitary evolution with Hamiltonian h, then if you look at this formula, these dots mean derivatives, so derivatives just take down Hamiltonian. You have just that the quantum Fisher information is 4 times the variance of Hamiltonian, and it tells you that if you want to if you put your quantum state in a box and wait for some time and measure it, and you want to learn how long it was in this box. Yes? This is this time estimation. Then you have this uncertainty relation that variance of estimating time is lower bounded by 1 over 4 variance of Hamiltonian. So this is the most, I would say, rigorous proof of time energy uncertainty relation, okay, where we have an operator and an estimator, and there's no problem with discussing whether there is a time operator or not. Okay, it's not relevant here. It's an estimator. Okay, so these are very useful tools. And now we think about the simplest model in quantum metrology, just phase estimation. So imagine we have a qubit which can rotate by an angle phi around the z-axis. And now you can consider different schemes of estimating this phi. So imagine you have these n qubits independent. Okay? So each of them you send through such a gate, and then you measure them independently. But you can think about a more sophisticated schemes where you send an entangled input state into these n channels and perform some collective measurement in the end. And you can ask yourself how well I can do. So using concept of quantum Fisher information, this problem amounts to answering the question, what is the maximum quantum Fisher information of output states over input states? Okay? So for this scheme, it's very easy to do because quantum Fisher information is additive on product states. That's why it deserves the name information. Okay? So then all you have to do is to find the optimal input state that maximizes Fisher information for this process, and it's not surprising that it's any state on the equator of the Bloch sphere because it changes the most, okay, with rotations. And then the quantum Fisher information for this n product of n states is n. It's case linearly with n. While here you can imagine this G8Z state or Nun state or something, which is a superposition of all qubits being in 0 plus all qubits being in 1. And then you have this n squared quantum Fisher information, which we call Heisenberg scaling. Okay, so everything is simple up until now. Okay, but now actually this scheme is not the most general scheme you can imagine if you just constrain yourself. I am allowed to use this gate n times. How well I can estimate phi? Okay, this is actually the most general scheme. It's a scheme which at first sight may look not that general, but it is because we assume that first qubit goes through our gate, and then we have arbitrary number of ancillary qubits with which this qubit could have been entangled initially. And then after each application of this gate, we can apply arbitrary unitary operation of all qubits. And in the end, we apply collective measurement. Such scheme, for example, captures this scheme because you can think that these V's are just swap operations, swapping the lines, and in this way making this scheme equivalent to parallel scheme. But it's much more general because in principle, by using these additional lines, you can model adaptive changes of your state after a few steps, depending on what you've learned up till some point, and so on. So that's why we call this adaptive, a most general adaptive scheme, because it allows for everything.
But then you have measurements during
No. You still do it here, but imagine that you have some ancillary qubit that only interacts here with this V, and then it goes trivially further on, okay? So then it doesn't matter whether you measured it here or in the end. There was some measurement result. Depending on this measurement result, you had some conditional unitary acting on the other qubits, which effectively amounts to saying that if I measured this, I did some conditional operation changing my states further on, okay? So measurement can be postponed until the very end. Okay? And apparently, if you ask for now the question, what is the maximum Fisher information for this phase estimation within this model, actually it happens that you gain nothing. So that it's still n squared as before, so as in this parallel scheme, or even worse, because it's the same formally if you just put these n gates one after another, just use a single qubit and act with u phi n times on it. Formally, it will give you the same Fisher information as this G8Z state because the phase again will be acquired n times faster if you act with this u phi on a single qubit. So somehow here, not much is gained thanks to adaptiveness, and if you want to go even further, you could say that not much is gained thanks to entanglement, because it's just if time is not a resource, but just the number of gates used, then equivalent you can use with a single qubit the same. You can achieve the same thing. Fortunately or not? Okay, not yet. Just a quick slide, how you relate phase estimation and frequency estimation. You just relate it by multiplying by t. So now our phase is omega t, and now we can ask the same question but concerning estimation of omega instead of t. And instead of saying that number of gate uses is our resource, we will say that the total resource is the total time, total interrogation time we will consume. Okay? So in principle, you can split your total time to like some number of gates lasting small t. Okay? And we will just say that the total interrogation time must stay fixed. So interrogation time means the time that we use this channel. Okay? And now if you write like this, then the equivalent of this n squared stuff is here translated to t squared, because t over small t is the number of gates. So this is this n squared as before. But now because we estimate omega and not t, then we have this factor t squared just coming from derivatives. Yes? And then this is what we can say about such scheme. So given total interrogation time t, capital T, with such a scheme, adaptive scheme, you cannot estimate omega better than 1 over t, which for some physicists seems trivial, but okay. This comes out from this approach rigorously. So now, the interesting things happen when you replace your unitary with noisy evolution. Okay? So instead of thinking that I have an ideal unitary, I say that I have some quantum channel, which I describe with Kraus operators that describe me also some decoherence processes. Okay? So for example, instead of considering this unitary, this rotation of the Bloch sphere, I can add dephasing that shrinks my Bloch sphere to Bloch ellipsoid. Or if I now think more in optical terms, I can think that previously my qubit was like this interferometer that gave me this phase phi, but now I add loss that I model with some virtual beam splitters in my interferometer when I lose photons. Okay. So how to proceed then? So we ask now the same question. Yes? So we are allowed to use these channels n times in this most general adaptive scheme. So what will be the maximum Fisher information? Okay? When we optimize over what? Here we can optimize over input state and over all of these control operations. These are our knobs. Yes. And now I believe that you can easily be convinced that this is a much more difficult problem to answer, because there is no explicit formula. I mean, there is a formula, but not so explicit for quantum Fisher information for mixed states. Okay? So if you have a channel that produces mixed states, then there is a formula for quantum Fisher information. Okay, so quantum Fisher information of mixed state is trace of this mixed state with symmetric logarithmic derivative operator squared, where symmetric logarithmic derivative is this operator here that you have to find out from this equation. Basically, it amounts to finding eigenvalue decomposition of rho phi, if you want to write it explicitly. So you can imagine that you can do it if you have explicit model, but to derive something in general is not that easy with this formula. But there is a beautiful theorem that tells you that if you have mixed states, you can think of purifications of these mixed states to some environment. Yes? So that you think of pure states for which the reduced density matrix is your density matrix. And now you can have of different purifications. Actually, we are speaking here about family of purifications, because we have rho phi, which is a family of states, and for each family of states we write like a family of purifications, okay? For which we calculate quantum Fisher information. And of course, if you take a purification in general, you can get more information, because there is more information in purification than in reduced matrix. But there is a theorem which tells that if you minimize over all purifications, so you look for the kind of least informative purification, you will find one for which the Fisher information is equal to the Fisher information for the actual mixed state. Okay? So this is a very nice result, and you may wonder whether it's useful. So, because maybe it is difficult to find these purifications. So in general, yes, it is difficult. But this result gives you a hint that maybe even if I cannot find the optimal purification, but a reasonably good purification, I will get a reasonably good upper bound on quantum Fisher information that may tell me something non-trivial. Okay? So this is a main message here, because this is actually the feature that we will use later on, and that will allow us to derive useful bounds. Okay? Okay? So, sorry. So now we go back to our problem. And now I will not give you all the steps of the reasoning, but I just want to convey this intuition that we make use of this minimization over purifications idea. And here we have these mixed states, and instead of talking about purifications of states, we will rather think about purifications of channels. So a quantum channel, you can also think that it's actually a unitary over a bigger space what you trace out. Okay? And if you remember derivation of quantum channels and CP maps and so on, you know that Kraus operators are not unique, and you can find different Kraus representations for the same quantum channel, and they differ in a sense because you consider different purifications of this channel. Okay? So you perform some rotations on your environment and so on. So now this idea of minimization over purifications of states enters here in a form that we will look for different Kraus representations of our channel. Okay, so we will think about different set of Kraus operators, and most importantly, this. So if you remember this derivation, then you know that these equivalent Kraus representations are connected with each other by coefficients that form a unitary matrix. So here the important thing is that we allow these coefficients to depend on the parameter we want to estimate, because this will be this essence that we change the information content in the purification. Okay, okay, and now goes to something, and then we arrive, by using these ideas, one can arrive at the following bound on quantum Fisher information. So, so it looks maybe a bit difficult at the first sight, but I want to stress that it's really it's really extremely simple, taking into account the complexity of the problem. Because we deal here with objects which are only objects like a single channel objects. So n is number of channels, but here we have like operator norms of operator alpha and operator beta. And operator alpha and operator beta are constructed from Kraus operators describing a single channel, okay? Single channel. So even though we talk about quantum Fisher information of the whole like entangled state of many particles and so on, we bound it with quantities that are function only on the properties of a single channel acting on a single probe. Okay? These dots here represent derivatives over parameter phi. Okay? So there is this operator alpha and operator beta. And this bound looks like this, and you see that you have a term that goes linearly with n, with number of gates, and quadratically with number of gates. And usually, if you take your quantum channel and you take a canonical Kraus representation for your channel and you plug it here, you will have this n squared term, which means that your bound is really not very useful, because you say that quantum Fisher is less than n squared, which we know already because for decoherence free case it was n squared. But if you manage somehow to find a Kraus representation for which this operator beta vanishes, so the norm of this beta vanishes, then this term vanishes, and you have a bound on your quantum Fisher information that scales linearly with n, which tells you that whatever tricks you do here, you cannot get better scaling of quantum Fisher information than linear with number of gates that you use, which will be a very powerful statement. Okay? So this is the history of this bound. So the first derivation of this was done by Fujiwara in 2008 in a setup with parallel channels. Then basically we and the group from Brazil understood this paper and translated it to physics. And then in this paper, we generalized this bound to cover this adaptive scheme, okay? Because initially it was just for this parallel scheme. So this is like this short history here. So now, if we come back to this adaptive frequency estimation task, we can write the same bound as for the phase and ask again for this maximum quantum Fisher information, how it will scale with the total interrogation time t, whether it will scale linearly or quadratically. Okay? So now, because we think about frequency estimation, time of evolution of our single gate is a parameter we can choose. Okay? So we should model our evolution using a differential equation, and we assume here that we deal with Markovian noise. So this assumption is necessary that we can really write these gates like independent gates acting at different moments, and that there is no correlations in noise. So we treat it like independent entities. Okay? So this is a general quantum master equation where the parameter we want to estimate is just a multiplicative parameter of this Hamiltonian, and then we have this general noise process. Okay? And now we want to understand what conditions this noise should have, that, for example, we are able to reach this scaling, and in what cases we are bound to this scaling. Okay? So this is now this general question I want to ask. And of course, now you can apply this bound that I mentioned before. Just replace n with capital T over small t, and put these alphas and betas for this particular channel. And now comes the important fact that because we consider this general adaptive scheme, the most general scheme corresponds to a situation where small t goes to 0. Okay? Because then we have more like adaptive steps for the same total interrogation time t. And of course, some of these operations we can make trivial. Okay? So this is like more general situation than imposing some finite small t. Okay? And that's why we are able to do something general, because we may now look at this bound and take the limit t goes to 0. Okay? And thanks to this, we are able to write Kraus operators explicitly in the lowest orders as a function of these Lindblad operators or jump operators that appear in the quantum master equation. And that's really nice, because before we had to play with these Kraus operators, and for each problem we had to solve it again and again. And now if we have this connection between Kraus operators and Lindblad operators, we can try to analyze everything in terms of explicitly these Lindblad operators that appear in quantum master equation. And now I will spare you the technical details, but the idea is now to look at these operators and expand them in time and look at the orders in t, okay? And ask what is the condition that this beta vanishes in a linear order in t, because this is actually enough in this derivation. And if you do it, apparently you arrive at a very simple algebraic condition. So you are able to make this beta vanish in this first order in t, which is enough to be able to neglect this whole term here, if your Hamiltonian belongs to a space which is spanned by identity, this Hermitian part of this L operators and I times anti-Hermitian part, because we want to have Hermitian operators here, yes? Because Hamiltonian will belong to this space. So there is a Hermitian part, I times anti-Hermitian part of L, and also you take the products of L's. And if you can show that Hamiltonian belongs to this space, you know that you will not get better scaling than T. So intuitively, it means that noise is rich enough to, to like punch your Hamiltonian from every side. Okay, you can think like this. Okay, of course, this is not the end of the story, because the fact that you get a linear scaling doesn't mean that there is no quantum enhancement thanks to entanglement. Still, there may be quantum enhancement in terms of a coefficient, which cannot be reached by using classical states or uncorrelated states. And we have also, numerical methods to calculate the coefficient here with a semi-definite programming, which is also easy to implement. Okay? So then the message is that, unfortunately, if you take like a random noise model, which is realistic, you will usually fulfill this condition that Hamiltonian will belong to this S. So, for example, if you take this dephasing model that I described before, what it corresponds to? It corresponds that your Hamiltonian is sigma z, and this dephasing is described with Lindblad, which is also sigma z. Okay, then obviously H belongs to S, and you have this scaling where Fisher goes linear, which means that uncertainty goes like 1 over square root of t. And also, you can derive the coefficient, which in this case is 2 gamma. For optical interferometry, now it's a bit more tricky, because I would like to think in terms of like that each photon is a distinguishable particle that goes through its own interferometer with the same phase to model, to put this problem in this framework of these gates. Okay? So formally, to describe it, I introduce like a three-dimensional space where first 2 dimensions represent the photon going upper arm, photon going lower arm, and the third state is needed to say that photon is lost. Okay? And if I write it like this, my Hamiltonian then for this interferometry is 1 minus 1, or maybe I should say 1/2 minus 1/2. Okay, but it's proportional to this. Now, and we have two noise operators which correspond to I lose a photon from the first arm, I lose a photon from the second arm. Okay? And now you can ask yourself the question whether this Hamiltonian sits in this space. So what do you think? Yes. Yeah, that's true. Because with L0 dagger L, you can produce 1 on the here. With L1 dagger L1, you can produce 1 here. Okay, and you have also identity, so you can mix them. Okay, even with these two, you can mix them with negative sign and have Hamiltonian. Okay. But here you see it's important to have these terms as well, to have this. And indeed, it's inside this set. And again, you can derive the bound with the coefficient, which in this case takes this form. And this is a very, very, appealing form, because if you just had 1 in the enumerator, you would have scaling which is 1 over eta n. Eta is the transmission of the interferometer, yes? So eta n means how many photons go through on average, yes? So simply 1 over eta n is the classical limit. So what you would get with like standard coherent light if you send in. So actually this enumerator, the smaller it is from 1, it is actually this quantum gain coefficient, the square root of 1 minus eta. So if you do any kind of optical interferometry with transmission eta, you know that by doing like squeezing, entangling photons, this is what you can get at most, square root of 1 minus eta gain in phase estimation. So these are maybe pessimistic bounds, but the good thing is that actually they give some gain, some quantum gain, and you can reach this bound using relatively easy strategies, like involving realistic quantum states. So for example, in this optical interferometry, this was this first like real life use of squeezed light to reduce the noise in gravitational wave detector. In 2011, it was done in this small interferometer near Hanover, GO600, where they were able to demonstrate that they reduce uncertainty, reduce noise by 33% just by sending squeezed vacuum instead of ordinary vacuum, while keeping other things unchanged in the sense of the power of the main coherent beam. Yes? So in this plot, this is some noise, okay, where they have this with squeezing, and this dashed gray line shows you what would be the bound if you had no squeezing. This dashed red shows you the bound corresponding to the amount of squeezing they actually had in this interferometer, and this solid red is a bound that is actually derived from this formula, which is like fundamental bound. So you could say that if they had devices that can squeeze light as they want or prepare any kind of entangled light, with this amount of losses that they have in this system, which was like 30-something%, they would anyway would not be able to go below this solid red line. So this is a good message, because it tells you that what experimentalists do is already optimal. Okay, so they should be happy because they use quantum features in an optimal way. So the optimal way actually happens to be the simpler one, the simplest one. Okay, and now you can ask the opposite question: what happens if this Hamiltonian is not in this space? And then I should skip these examples here, because tomorrow morning Jiang will will give a whole talk on using quantum error correction to recover Heisenberg scaling in metrology. So actually, I just mentioned this simple case where this happens. So if you have now, again, the same Hamiltonian, but you replace your dephasing with kind of perpendicular dephasing, so it's no longer sigma z, this L operator, but sigma x, then you can clearly see that you cannot produce sigma z out of sigma x and products of sigma x and identity, okay? And then indeed, these are the papers where people were studied this scheme, and they were showing like quantum error correction like schemes that allow you to protect against this noise and reach this Heisenberg scaling. But as I mentioned, I will skip it, not to spoil tomorrow's talk. And finally, I will, okay, now I mentioned explicitly. So this is the fact that was proven in this paper. So unfortunately or fortunately, we were not clever enough to prove it in our paper. So this is like now if and only if statement. So in our paper, we can find the proof that if Hamiltonian belongs to S, then we have the scaling in T. And in this paper, we can additionally find the proof that if Hamiltonian doesn't belong to S, one can provide explicit quantum error correction protocol to reach this T squared. Okay? And again, I skip it and just now mention some applications. So I should be finishing in 5 minutes. Yeah, okay. So I just mentioned that maybe something which is not obvious to you, that you can really apply these ideas to different setups. So you can, I just described something which we call linear metrology. So where Hamiltonian acts independently on each part, is a sum of independent Hamiltonians, and loss is an independent decoherence process or decoherence process acts independently on each particle. But you can think of a models where you have like something called nonlinear metrology, where Hamiltonian is a sum of Hamiltonians that acts on some subsets of your particles. Like you have some nonlinear interactions, like two-body interactions or three-body interactions, and you have some you have these nonlinear things happening both in the Hamiltonian part and also in this noise part. Okay, so I graphically represent it like this. That, for example, you have like three-body terms in your Hamiltonian evolution and two-body terms, like two-body losses, for example, in cold atoms or some. Okay? And actually, you can then play with these boxes that I described to you, and you can again show like quite general formulas that tells you that if you are able within these setups to show that Hamiltonian again can be spanned by these L operators, then you can show that the scalings are bound to scale in some way with this number of particles here. So like the scaling here is like 2 times nonlinearity of Hamiltonian minus nonlinearity of noise. So in particular, if there was no noise, you have this n to 2k scaling, which is known in nonlinear metrology papers. But here we also take into account noise. So what are the plans for the future? So why this is not a grand unified theory period, but it has some, there's some work to do. So the main assumption here was this Markovian noise. So in other words, it's a noise where there is no correlation. So in this scheme, I could think of situations where there is some time correlation between noise. Okay, so these boxes are not really independent. Or I could think more in terms about spatially correlated noise. So like, I know, fluctuating magnetic fields with some correlations between them. Okay? And then these results, they do not apply directly. You have to think something. So for example, a practical problem is stabilization of atomic clocks, where in fact you have something which can be described more or less within this scheme. So like you have this local oscillator which fluctuates, and it also has like some correlations in its fluctuations, and you want to stabilize it to atoms by measuring it on the way. So we did some work in this direction, but this work is far from finished. And at the moment we are thinking about like developing a general theory for situations where you have these correlations, but we will add assumption that these correlations are local. So that you can think that these time correlations only happen on some small time scale or on some small spatial scale. And then intuitively, you can expect that maybe some more efficient description, like using matrix product operators, could be involved here to deal with such problems. And this is like work in progress at the moment. So this is the take-home message, and thank you for your attention.